thank you, everyone. Since like we have Jason, so before we start, I want to ask like how we want to do the Q&A here. Do people raise their questions?
I think we can have the Q&A session at the end of the presentation.
Okay. Oh, okay. Sounds good. Sounds good. Yeah, good afternoon, everyone. Oh, I'm very glad to be here and present, as I mentioned, like the recent work in optimizing the latency sensitive queries using Presto and Alluxio. It's a stack we're collaborating with Facebook. And this stack, most of this part of the deck is built from my previous talk in a meetup in PrestoDB. And this is the agenda today. I want to give an overview first about what is Presto and what's the problem we're going to solve with what kind of architectures. And then I want to present the challenges we see, and that's the reason we want to re-architect the solution. I will talk about the performance and I want to give some deep dive into Alluxio. So for this particular talk, we will focus on the stack of Presto and Alluxio as a solution to certain queries, to certain workloads. If you are not, I'm not sure how many people know about Presto for the audience here, but it's basically a distributed open source SQL engine developed mostly originally in Facebook, but now it's open source and there are many companies behind. So if you are a little bit more familiar with database, you may heard like Oracle database or MySQL. So Presto is something similar to that, except it's running for the OLAP workloads. It's doing analysis, not the transaction. You're not going to use Presto to run transactions, but you can run a lot of analytics work. For example, the query we show here is to select certain things from a table with a certain criteria. So this is a very, very simple SQL query. And the advantage for Presto is that it can be very, very scalable. I know like in normal cases, you may just need one instance or few instances to run on MySQL workloads. But for modern data platform, you often have the needs to store and to analyze the data on the order of petabytes or at least the terabytes. So that's very common for the modern data platform. You need a very scalable system. You can distribute the workloads across hundreds of thousands of different nodes rather than just like a few nodes. So that is why Presto is designed and why people are using Presto. So today, a lot of companies in the Silicon Valley all across the world, especially in the internet sector, they use Presto a lot in the backend. There's a lot of companies behind. They are using this, but also building this. So let's take a look at how Presto is used in Facebook. Now, more than 40,000 servers are running Presto at Facebook and scanning more than 1 exabyte, that's 1,000 petabytes, which is 1 million terabytes per day. You can see like how large the scale it's processing. And it's like more than 80% of the workloads is about the new ETLs. Read the data, do some processing, and write the data back. And this is the typical use for Presto at Facebook. If you want to zoom in a little bit, if you are a little bit new to Presto, this is its architecture. You have the workers and also the coordinator. That's the different components of the Presto. So it also depends on something called a high meta store to read the information of the tables. High meta store is a dedicated service serving information like that. And data will be served from a data store like HDFS in a data warehouse similar to Facebook. In the clouds, many people run this in S3 or GCS and similar data services. So the SQL queries goes to the coordinator, and inside the coordinator, there are the planners, optimizers, schedulers, and they will split the work across different workers, across certain policies like using workload balance, the policy to assign the different work or split up the work into Presto Workers, and you can have thousands or hundreds of different workers to for your query. If the query is very large, you can involve a large number of workers running for the same query. And then the workers will do their job, and then in the end, we will aggregate and do certain computation to have the result written back for the user. And this is from the architecture's perspective. From the services perspective, the HDFS is responsible for serving the data, or similar services like HDFS or S3 is responsible for serving the data. Open the file, read and write the data blocks. And high meta store is responsible for serving the table level information, like what is the table, what is the schema for this table, how many columns, what type of each column, and for each partition, how does this partition correspond to any file on HDFS or similar data storage. And Presto is a service, SQL processing service built on top of the other services like high meta store and HDFS. So it's a very common technique for you to think about, like, how can we further optimize the performance. And for this talk, we're going to focus on the particular technique we developed or collaboration we have recently, which is to add the data caching capacity into Presto. So caching is never new. It has been practiced in computer science for so many years, for over maybe 60 years, 50 years. It's a common optimization technique to cache the working data set closer to the computed nodes so that you have lesser trips to the remote storage and will help the latency and reduce the I/O. This is so commonly used. You probably can see this kind of ideas throughout all computer science systems. So what we want to build here is to add a new data caching layer closer or local to the workers. So instead of having the data always going to HDFS and return from HDFS, you go through this local cache layer first. And this cache layer will check the local SSD and see whether it has data already cached. In case it's cache miss, we don't have data locally, this data cache will go to HDFS, fetch data for you, for the worker. Or the data will just go to local SSD directly and serve data back to the workers. So this is how it works in a nutshell for Presto with data caching. Another part is to another very important factor to have a good performance with Presto. If data is local, then the next time when we run the same query or a similar query touching the same data, can we guarantee the same query will go to the same worker so you can have the data locally? Or even you have worker A, which has local data on that node, we may schedule the task to a different node called node B, which may or may not have the data locally. So that's another way we need to think about in such a system, in such a distributed SQL engine system, how we can guarantee that when we are doing the node scheduler, it will also optimize for the data. So to get the data from the same node. This is what we call affinity scheduling. Affinity scheduling in this context refers to something when we schedule the node, like this is the task for a split of the task. We will check which node, we'll think about it, which node to assign to, rather than just randomly select one worker to run this task. And the way we do this is to really get the path, the file, and we hash the file, which in Java language is a hash code, and we modular this to the number of nodes. So in this way, for the same task, reading the same data, it's likely we will assign this same task to the same node. So this is a very simple idea, and a lot of different systems are practicing the similar ideas. But in this way, we are doing this as best effort because node can go off and nodes can go on. It's possible like we lost the node in the middle and we don't want to just permanently blocked because we lost the node or there's a new node added. So this is the best effort. And we will also consider how to take into work balance, the load balance into this consideration. Okay, so we talked about the scheduling, the affinity aware scheduling. Then there are different options to have data cached. So for Facebook team, originally they have their internal caching library, and like Facebook has a huge engineering team with a lot of assets accumulated past over years. They definitely have something you can do with the caching capacity. However, there's the caching library is not open sourced. And for Presto, it's a fully open sourced, and they do really want to build another caching layer underneath Presto with the open source solution. And the second option is to leverage some open source solutions like Alluxio. So that's why actually we choose to go this way. And the third option is to build their own caching library. But because they're, like, for example, the expertise for Presto team is really optimizing the computation, optimizing the planners, optimizing the SQL in the SQL land. And they do believe like what we do in the past few years in Alluxio can be a good complementary to this project. So we decided to go together. So originally, there's a baseline inside Facebook Presto called file merge caching. This is a very naive solution. It can just copy files from remote storage to the local storage and merge files in local storage to keep the file count low. So this is called file merge caching. This is a very naive way to do cache. You can probably implement this in a relatively short amount of time, but also the downside, the simplicity is the upside. Downside is you have a lot of advanced features. These advanced features are hard to support with this file merge caching. So originally, Facebook team is testing file merge caching using Presto. And one thing we found is the cache hit rate varies a lot. Sometimes it goes up to over 90%. Sometimes it goes down to below 10%. And you see that varies over the whole day. It's varying a lot. So that's why the simple cache is simple to implement and something good to start, but that's not how you want to use the cache. The lessons learned, and that's why Facebook team goes to Alluxio to me and saying, okay, let's collaborate on this. We want a Java-based open source solution. And we, instead of having a file, having file as the granularity to cache, we want a smaller granularity, a finer granularity caching solution, like based on segments, smaller units than files. And we want to implement pluggable eviction and policies like LRU or LFU or whatever caching replacement policy you want to. And we want to configure different aspects like the caching size, resource usage, eviction policies, all this to be configurable. We also want the details that's across the entire cluster, so it's easier for developers and DevOps to maintain and to monitor the health for the workloads. Caching should not be the point of failure in case something goes wrong. You should always be able to fall back to an original remote data storage and implement some asynchronous operations. And file management at the disk level can be, that's something that we can leverage. And the one stretch goal is to have because this is SSD, you want to avoid the wear out for SSD devices. So there should be some super limiter to avoid the endurance issues. Okay, so all these requests come to us. And we said, okay, no problem, let's work on this. Let's work together to get Presto another caching solution. On the other side, before we go to more details, I think if you go through some, like maybe some interview about how to implement the cache, what are the advanced features you can do for a cache, this is the good list, because this is really motivated by the real production workloads. And it's also really tested and motivated by one of the most, I would say, most adversarial workloads in the world, which is serving Facebook workloads. Okay, so let's take a look about the performance after we have this solution together. After we installed Alluxio as a caching layer for Presto, now we're running, this is the benchmark we're running on the 600 nodes, and with 460 gigabytes per node configured to use this data caching layer. And we use the default LRU eviction policy. Previously, I mentioned the naive caching is using file merge. So the basic unit is a file. But now we have the smaller granularity with the 1 megabytes as a block size. And if you read data and store data, you can evict at this granularity. And also because we have a finer granularity, it's also emulating better the workloads, and you can use the cache space much more efficient. So that's one thing we learned. Essentially, with this new caching solution, we have seen a lot of new good results for the query we care about. So the caching means, in the second row, the caching means the solution, the performance with the caching solution. And the third row, master, means we have just run run Presto without the caching solution. So the benchmark results shows that for the mean and for the P95 percentile query, you see a dramatically change. The mean query latency is improved by 30%, and P95 we see close to 50% improvement after using the caching solution. So this is really ideal they're really, really happy about this collaboration results. And we run the data size read from, again, this is a huge 582 terabytes data. And for the caching branch, we cached 251 terabytes and saving scan about 57%. And the cache hit ratio, you see, it's pretty stable. Most of the time, it's higher than 90%. Occasionally, we see a drop down, and we are still working on this, and there are a few issues we're addressing to further keep the high hit ratio stable. Okay, I have talked a lot about this Presto Plus Alluxio caching as a solution for distributed data SQL queries. But now I will go to a little bit more detail about what we do how we build this Alluxio data caching layer for Presto. Before we go there, I want to give you a very high-level introduction about Alluxio. It's basically a data orchestration for the cloud. That's what Alluxio is built for. And it translates the access to optimal storage APIs over a slower network. You can think in the data stack, we have the compute sitting on top of Alluxio layer, and we have the storage sitting beneath Alluxio layer. Alluxio is connecting compute to storage. And this is the new layer we invented. We call this data orchestration layer. And within this layer, you can do a lot of different advanced data policies. You can, for example, caching, for example, setting a TTL, and you can add data translation. So you can translate different API calls to the same data abstraction. And you can also build abstraction in the southbound, beneath, to connect to all kinds of different drivers, to connect to all kinds of different storage using different drivers. So you can mount S3 into Alluxio space, you can mount a HDFS into Alluxio space. In the same logical namespace, we expose this logical namespace to users. So users and developers, they don't need to care about what is beneath. And this will simplify the maintenance and development a lot. It was a research project before called TagYang from UC Berkeley AMT lab by a Ph.D. and our CEO, Haoyang Li, and was open sourced. in 2015, we created a company, commercialized this Alluxio, and we got the top VC from Silicon Valley, including Andreessen Horowitz, to back our journey. Along the way, we get a lot of recognitions. I list a little, some here about the awards we're getting. So this open source technology has been used by many different companies and in different sectors, from financial services to internet to consumers and retails to telco and travel. You can see a lot of big names on this list. I won't go through the details. But essentially, with Alluxio, you can deploy we see different ways to deploy Alluxio. So you can have on-premise data warehouse, and you can also deploy Alluxio in the cloud. And it's up to you, and there are different ways. For this particular topic today about Presto, this is the architecture we're using. So Alluxio is providing a caching file system layer to the Presto worker. And each Presto worker, you can read and write data through this caching file system. And if it's uncached miss, we have the code path to go through the external file system. On the cache hit, you go to the cache manager and go to the local storage. So these are some implementation details and optimizations we did. For example, as I mentioned previously, one key optimization is to cache files in fixed sized segments. And in the computer science terminology, when you have scenario like this, it is often called pages. So in the operating system, you have the memory page, and it's very similar to the concept like this. You have different files with different variable lengths, but you segment this into fixed size. So it's much easier for memory system to manage and to optimize for hit ratio in this case. In our case, we have this as not for memory, but also on SSDs, and 1 megabytes is the default size. Another key optimization is to store pages off heap. If you are familiar with Java, you may know there are two different concepts. One is on heap, one is off heap. If something is on heap, that means you're using JVM's memory. And JVM memory, now in the modern days, you can allocate maybe a few, maybe 100 gigabytes to JVM, but that's perhaps the most you want. More than that, JVM is not very good at handling more memory. However, without having enough JVM on heap memory, you may see GC or garbage collection kicks in a lot. So that's one issue you often see running Java-based applications. But nowadays it's just so popular in the data world. Entire Hadoop world is built on top of Java. Presto is built on top of Java. Spark is built on Java. Alluxio is also built on top of JVM. So all this JVM is very essential. So there's a different way. Instead of always using a JVM's memory to store data, you can also allocate memory resource or storage resource externally, and this is called off heap. So in our case, we also do this trick. We use SSDs, so that is not from JVM memory resource and significantly can reduce the pressure or avoid adding more pressure to JVM, Presto's JVM. So we have the highly concurrent and stress-safe design for this cache. Essentially, if you want to have a highly concurrent workload, Presto, by the way, is designed to be very, very concurrent. So you may see a lot of threads are running together at the same time, reading data or executing on the data they read. So as a data layer for this execution, we also need to be very concurrent. So that means we need to be thread safe too. On the same JVM process, you have to guarantee no deadlock or no racing happens. Otherwise, it's unsafe for Presto to run on top of a data layer like this. So we implemented a lightweight and fine-grained locking scheme inside Alluxio local cache. And this is actually really, really tricky. I can show you a lot of my experience. I have been doing on this. I did my PhD research on this, and I write code many times in this language, but still I would say that's the hardest part. The concurrent programming, concurrency programming is the hardest. Multi-threading programming is the hardest. It requires to think very clear about what you're doing and how you can coordinate across different threads. So it's pretty hard, but it's very fun to me. Yeah, but in the end, we come up with this lightweight and fine-grained logging scheme, and it's very efficient. Other than that, we also have some other implementations of optimizations, including a pluggable cache replacement policy. We implement LRU and LFU for Facebook to choose, and we implement the pluggable cache storage options. A naive one, which we are using, is a local file system store. So each page, 1 megabyte segment, corresponds to one file on the disk. And we fully understand that sometimes you're having too many pages or too many files in the same file system can be inefficient. So another option here, we also implement some called RocksDB store based on an embedded key value store. So in this way, we can avoid having too many segments as the files stored on the file system or pressuring the file system for the performance. And the async cache writes is also a optimization added to this implementation. So in order to handle the bursty cache writes operations, we can queue the writes requests into a background processing queue. And in this way, you can handle the bursty workloads. So having a queue is a common optimization, or put something in async mode is a common practice and optimization for performance. It's basically, you can, if you put something in the async mode, you quickly insert the query you want to complete into a queue and then go back. Later on, you have a background processing threads to pick up from this queue and complete these tasks for you. And this is just like a very common one to optimize. Another thing we realize is very easy. It's relatively easy to implement, but also very critical actually in reality, which is to add a lot of performance metrics. And this is actually something I've learned working with Facebook engineers. It's really interesting to see when you're operating in the large scale, they're running this with thousands of nodes. It's very hard for you to really monitor, to notice the failures on a single. If you have a failure on a single node, it's just very hard to see. So you have to design the performance metrics, the state metrics, and the throughput metrics carefully, so that when you see the aggregated metrics, it's easier for you to tell, oh, okay, I know there's something goes wrong in my cluster, in my operation. So I need to zoom in, I need to go down to that particular node and check out what's happening there. Having the performance metrics is really, really important. I will say this multiple times. It helps us, saves a lot of time to debug issues and diagnose these performance issues. So here are a few ongoing developments for this particular collaboration. We're working on a schema-aware, the schema or table partition level cache quota. And also I'm working on the in-memory page store. So for certain workloads, you may want to just have all the data in memory rather than having data in like SSD. So it really depends on the workloads, but we do see like users, for certain users, they're willing to pay more resource for better performance. So the fully in-memory page store is something we are also we're also investigating. The last is the semantics aware of caching. So that is really a very advanced feature based on the semantics for the file. I can tell, oh, this is a Parquet file, this is an ORC file. I may know the footer or the header, how large are the footer and header, and how we can store this footer and header, cache them and analyze them beforehand, so I can understand the workloads better, or I can prefetch, or I can do some other fancy optimizations. So these are the future works we are thinking to collaborate in the future. So actually, there's just like recently they just added one new feature, which is very interesting, that add a TTL to this data, to the client side data, so we can erase data like after data is erased. We can say, okay, we want to purge the data too from the cache, so the data is more consistent from the source of truth. Yeah, so this is some simple way. If you are interested, this is something you can learn from the blog. We wrote a blog together with the Facebook team about how to enable the Alluxio data caching in Presto. And here are the instructions you can follow. Okay, so I've spent most of my time talking about Presto with Alluxio data cache layer, but there's also another option here, is to use Alluxio as a full bloom system. Alluxio is a full functioning, full feature distributed system. So with the local cache library, you can achieve certain like a speed up, acceleration, and reduce data I/O for sure. But if you want to have a more control, more advanced features, here are the things you can do, including the fine-grained control on the working set and the metadata caching and the syncing. And with the data transformation services, you can transform, you can convert files from certain format to another and decoupled from how they are stored. We have the data migration services too, so you can migrate data from HDFS to S3 based on or something similar, based on your budget, based on your data access pattern and data policy. And also we have the familiar file system CLIs, so you can just control your data. Oh, I want to LS my data. So I can see which files are cached, how much of the data are cached. So if this is embedded solution inside a Presto like a Presto, it's hard to check. But with a a full feature file system, you can run CLIs, client side commands, to check this out. You can go to the link below to check out what you can do with the file system, Alluxio system.